Okay, we begin our seminar, and today our speaker is Daniel Hauer from Sydney, Australia. Please.
I think the title is a little bit different, not only fundamental gap conjecture, it's, by the way, fundamental gap conjecture and log-concavity. But I somehow forgot to modify the title. But firstly, thank you so much for the invitation, and that Daria, thank you so much. And also I want to say it's a great honor for me to speak here and to present my results. So you already, or some of you have been probably at the Centennial Conference for Ladizhenskaya Wien, but one second, I think that is the wrong slide because there is Ladizhenskaya Conference written. Let me just check. 1 second, please. I have to.
Okay.
I think that is the wrong slides because I prepared my slides. So that is the right one, yes. Excuse me. Okay, let me start again.
Okay.
Okay. Okay, so I was thinking that I was taking the wrong slide. Okay, thank you again for the invitation. And if some of you have probably already heard my first talk at the Ladizhenskaya conference, and so for you, some parts might be repetitive, but I definitely give one important proof, which will be quite different. And the reason is because this time what I want to do is I want to emphasize on the log-concavity on the fundamental gap conjecture. So I will explain for those who did not attend the first talk, which I gave at the conference in July. I will start nevertheless from the beginning. So I will introduce what is the fundamental gap conjecture. Okay, the results which are I present here, this is with my team, my Australian team. I'm German, so an Australian immigrant, but the team is with Ben Andrews and Julie Kladeback. So we are, and Julie and I, we got now a grant exactly on this problem. And so we are very blessed or fortunate basically to get now money from the government to continue our research in this direction. So let's start with the classical eigenvalue problem, which is the main object basically for my talk. So here alpha is a real number, and that is a parameter which you see in the boundary condition of this elliptic problem. Omega is always assumed to be a convex domain, very important, and bounded. So then when the potential V is in L infinity, we know that the Schrödinger operator has a discrete spectrum. Okay, and so basically, so there are eigenfunctions, and lambda alpha j are basically the corresponding eigenfunction for this Schrödinger operator equipped with this type of boundary condition. So d nu is the directional derivative in direction nu, so also called the normal derivative. And so you see that the normal derivative must be proportional minus alpha phi alpha. Okay. So we call this actually when alpha is not 0 or infinity, basically, then we call this the Robin eigenvalue problem. So how do we get the first eigenfunction? We can get the first eigenfunction simply by looking for the Rayleigh quotient and minimize this quotient here into the other eigenfunction we get through a min-max formula. So we can derive them either using functional.
Daniel, is this, should it be plus in the numerator?
Yeah, there is a plus missing. Very well, very good eye. Before the alpha, there must be a plus. I agree, I lost it. You're right. So that is the first, you know that minimizing this quotient, which we call the Rayleigh quotient, derives the first eigenvalue. The next one would be a min-max formula and so on. which cuts out basically the first eigenspace and so on. So what we know from the
excuse me, one question more. What is the space where you minimize phi? Yeah.
Okay, phi is, I can choose here H1 of omega. Yeah, but I choose here C1 of omega bar, since omega is Lipschitz. This
okay, thank you.
Is dense in H1, so it's not a problem. Yeah, it's good. So, and phi alpha, the first eigenfunction, what we know is that this eigenfunction, so the minimizer of this minimization problem of the quotient, is a strictly positive function, basically. And so we always assume that the eigenfunctions are normalized. So sorry, there is a z, but this, forget about this z, there is some mistake typo. This should be, this is a 2, which should be here. So it's normalized with respect to the squared L2 norm, okay? So what we have then here for different alphas, we have in alpha 0 that we get homogeneous Neumann boundary condition. And when we divide by alpha, for positive alpha, and we let alpha tend to plus infinity, then you see that we recover Dirichlet boundary condition, actually. So that is the reason why when you see later in the index where alpha is written, and you see there an infinity with phi alpha, then I mean Dirichlet boundary conditions. Okay, and in the middle, you see Robin boundary condition. So you can see the Robin boundary condition basically as an interpolation between Neumann and Dirichlet. And in fact, what we have is that the eigenvalues, so for fixed alpha, for fixed j's, so the first, the second, the third, and so on, that they are actually increasing when alpha increases. So you have exactly this sequence of inequalities. So you see that the Robin eigenvalue is squeezed between, the Neumann eigenvalue and the Dirichlet eigenvalue. Yeah. So that's another reason why you can see the Robin problem is basically the interpolation problem between Neumann and Dirichlet. So why are we interested in studying eigenvalue problems? So for this, I can give a very, very long list probably of applications. So here are just a few. So the Laplace eigenvalues, they appear, for instance, in vibration modes in acoustic of a thin membrane with a fixed boundary are given by Dirichlet boundary conditions, Dirichlet Laplace eigenfunctions. And then as electron wave function in quantum waveguides. Or we simply use it as an orthonormal basis of L2. And why? Because we can then rewrite the solution of the homogeneous heat equation with this type of boundary condition.
I'm sorry. And what is the difference between waveguides and quantum waveguides?
Excuse me, please?
What is the difference between waveguides and quantum waveguides? Is it the same?
Quantum waveguides usually assume Dirichlet boundary condition.
Okay, thank you. Thank you.
Thanks, I also learned something. Okay, so another reason is why we're interested in the eigenfunctions is because you see, and the eigenvalues you see basically that you can rewrite the solution of the heat equation with this Robin type boundary condition explicitly as this Fourier series. And then the first eigenfunction.
Yes. The previous slide, please. There are minuses in exponents.
Yes. Yeah, there are minuses in exponents.
Minuses, surely.
Right. Yes. Excuse me. There are minuses. You will spot every typo. Thank you so much. Okay. And the first eigenvalue, if there would not be a minus, then we would not have exponential decay. The first eigenfunction provides you with exponential decay in the.
I'm sorry. Now I don't see why domain is convex. Why is convex?
The convexity comes later. The convexity is assumed at the beginning. All these conditions, they still hold for any omega. But when you speak about the important crucial property log-concavity, you can only, it makes only sense in a convex domain.
Okay.
Okay? Okay, so then you know, okay, exponentially, the first eigenfunction appears here in the Poincaré inequality, which you have. And another reason why actually now the difference of two eigenfunctions play a crucial role, was discovered in a paper by Hatfield and Papageorgiou in 2015. They discovered that it plays a crucial role in the estimates of the costs of the algorithm in quantum computing. So it was a crucial size, basically. And so what kind of geometric properties phi alpha has? So let's look when the potential V is 0, because then it's much, much easier first. So for the Dirichlet problem, we know by a very old result by Lieb that the first eigenfunction, so here you see phi infinity, that's because alpha is basically tends to infinity, is log-concave. Yeah, so that's a very old result by Braskamp and Lieb. When alpha is 0, the first eigenfunction is just constant 1, because we normalized it. Yeah? So again, it is log-concave. But what is known about Robin eigenfunctions? And this was actually until 2020, one did not know really what happened there. So there was a very big gap. And it is natural to assume, so one function is constant, and so the Neumann function is constant, the Dirichlet eigenfunction is log-concave, that the Robin eigenfunction should be also log-concave. Yeah. So what does it mean log-concave? You know that the first eigenfunction is positive, so I just dropped the index here, and so it makes sense to write log of phi. For a positive function phi is log-concave is if log of phi is concave. And so you have exactly this inequality. So phi is log-concave. If you take the exponential in the concavity inequality, then you get exactly this inequality here. So and the important property is that when a function phi is log-concave, then you see at the inequality that the level sets are convex. But the opposite is not true. Yeah. So you can say, okay, phi is log-concave, so you get the level sets are convex. So why is log-concavity so important? That's an important why actually I'm interested in log-concavity. Well, I told you already before, the main task or the main problem where I'm actually interested is the fundamental gap problem. So the fundamental gap conjecture was firstly formulated by Michael van den Berg in 1983, who said, okay, we have a bounded convex domain omega and a convex potential V. Then he claimed, or he conjectured, that the difference of the second and the first Schrödinger eigenvalue equipped with Dirichlet boundary condition, that's the reason why you have here an infinity at the index top, must be bounded by below by 3 pi squared over d. And d, capital D, is the diameter of omega. Yeah. So, sorry. So this is again, it's the difference is called the fundamental gap, or the spectral gap between the second and first. Okay, why is the fundamental gap so important? So in quantum physics, basically the Schrödinger eigenfunction models the motion of an electron in an electric field generated by a nucleus exactly with one proton. And so the fundamental gap exactly describes how much energy you need basically to an electric, as an electron changes the energy level, it emits a photon. And this photon, basically the emission, can be measured by the fundamental gap. Then I said already Hatfield and Papageorgiou, they found this, that the convergence rates basically depends exactly on the fundamental gap. But also the fundamental gap is used in numerical methods for large eigenvalue problems. Yeah? So now one can of course ask, okay, I have here the fundamental gap, but why is it 3 pi squared on D? Well, when you go in dimension 1 and you take the zero potential, then you have the Dirichlet eigenvalue problem on the interval. Yeah, from minus d on 2 to d on 2. So you assume homogeneous boundary condition. So then you can, from this ODE, explicitly compute what phi is. Yeah, that's a sine and cosine, and they have an amplitude, and the amplitude is given by the square root of the lambdas. So you get here that all the eigenvalues are exactly, can be computed explicitly, and they are n squared times pi squared over d squared. So if you apply now this formula to the second and the first eigenvalue, you get here exactly that this is 3 pi squared over d squared. Sorry, so there is a square missing, Alexander. You missed. Okay, so that's the reason why you get this number here. Okay. So the fundamental gap conjecture was independently after Ben-Gurion suggested by Eschbaum and Ben-Gurion, from Vandenberg was suggested by Eschbaum and Ben-Gurion in 1989. And again, and also by Yao, by different conferences. And one can see that they did not see the papers basically from the others. So, but Eschbaum and Ben-Gurion proved the fundamental gap conjecture in dimension 1. When V is not only a convex potential, it must be in addition symmetric and single well. Hauer partially removed the symmetry assumptions, allowing single well potential with a minimum at x equals 0.
Excuse me.
Yes.
If it is concave, it should be single well, but maybe here is not the concavity is not assumed, or also assumed.
No. They are convex, actually. So the single well is like this. And then one times you want symmetry, so really you have point symmetry, x symmetry. And then so what Hauer did is that the single well, but it could be, as you said, it could be basically like this.
Yeah, but okay.
Yeah. And the first person who
I'm
basically...
sorry, it is new papers or maybe not new. Or
I did not understand the question.
Юр, попробуй по-русски сказать.
Ну, это какого года работа? Вот я последний.
Ну, потом ты увидишь.
Ладно, все, хорошо.
Okay. Alex, can I continue, or is there a question?
Yeah, okay. The question was, what year were these papers?
That were the first, basically the first contribution to solve the conjecture from Vandenberg.
Okay.
Yeah, and the first one who, for convex potentials, solved the fundamental gap conjecture in dimension 1 without any additional assumptions. So not that they are single well or symmetric, or that the minimum must be attained at x equals 0, was done by Richard Lavin in 1994. And he did actually the Neumann case and the Robin case, and the Dirichlet case, excuse me. Yeah. So in higher dimension, Banuelos, Mendes, and Hernandez, they proved the fundamental gap conjecture for the Laplacian in higher dimension. And Davis and Banuelos and Kröger, they proved it when omega is in R2 but symmetric, the convex domain. And so then there were a lot of papers given with non-optimal bounds, so non-optimal lower bounds. So you will see that these numbers pi squared over 4d squared will change. The first contribution was done in 1985 by Singer, Wong, Yao, and Yao. And then there's also another paper by Yu and Zong. Yeah, so they improved this slightly, this lower gap. But it took quite a while from 1985 until 2011 until the fundamental gap conjecture was completely proved for bounded convex potentials in any dimensions, you know, of the Euclidean space by Ben Andrews and by Julie Clutterbuck. So why is log concavity so important? Because let's show you the following result. What you can show is the following. Let's assume lambda 1 alpha v, so it's the Schrödinger operator. We have here the Schrödinger operator, but that's the first and the second eigenvalue of the Robin eigenvalue of the Schrödinger operator. Okay, where v is just the potential, it must be just L1 and bounded from below. And omega is a convex domain with diameter capital D. So then the assumption is as follows. If the first eigenfunction for the Schrödinger Robin operator is log concave, then you get that the fundamental gap is bounded by below by pi square on D square. Yeah.
Uniformly with respect to alpha.
Yes, that's exactly the point. Yeah. I come to this, Alexander, give me a second. So how do we prove this? The proof is really very short and very nice. Is you cook up an auxiliary function v, which is given by this quotient. So you have above the second eigenfunction, and at the bottom in the denominator, you have the first eigenfunction, and you have 1 times e in the power of minus lambda alpha 2, and in the bottom e in the power of minus lambda 1 t. So this equation satisfies a parabolic equation with a drift term. So you have here the heat equation. So v dTv is equal to the Laplacian of v plus 2 times, and here you have the log of phi, but the gradient of the log times the gradient of v. So that's your drift. So what type of boundary condition do you have? So when you compute the Neumann derivative of v, then you have to apply the quotient rule. So the first terms, which are t dependent, of course, they are just taken out. But then you have to apply the quotient rule of phi 2 divided by phi 1. And so you get your d nu of phi 2 times phi 1 minus phi 2 times d nu of phi 1. Phi 1 and phi 2, they satisfy Robin boundary conditions. And so you have to apply this where you have the normal derivative, and you get your minus alpha of phi 2 times phi 1. And here on the right hand of on the right side of the quotient, you have that this is plus alpha, phi alpha 1. And you see that they cancel each other out. Okay, and that's equal to 0. So you see that V solves a heat equation with a drift and Neumann, homogeneous Neumann boundary condition, constant for any alpha or for this alpha, yeah, where you test the eigenfunction. So now we assume that this vector field X basically is log concave, and that it has actually a modulus of contractions, since it is, so the modulus of contraction is generally given in such an inequality. So you have this dot is the dot product, the Euclidean dot product, and you say a vector field have a modulus of contraction if there exists a function omega defined on a closed interval 0 to d on 2 in R, such that this inequality holds. But since we assume that phi, the first eigenfunction, is log concave, the omega is satisfied by just taking it 0. If this is the case, then we can cook up a modulus of continuity for this V. And this is given explicitly exactly in this case. So this is an old result from Ben Andrews and Julie Clutterbuck. They have basically used this to prove the fundamental gap conjecture in the Dirichlet case. But they were a priori interested in modulus of contractions and gradient estimates for heat equations. And from this theory, so they were classifying basically the modulus of contraction by using the gradient estimates of the heat equations by using such kind of modulus of contractions. So, and when omega 0, as I said, you get exactly by this phi a modulus of continuity. And modulus of continuity means that for every x and y, the difference vyt minus vxt is dominated by this function phi. And here you have y minus x divided by the modulus of y minus x for every t larger than 0. So then you take the supremum between all x and y and you use the definition of v. V was exactly this quotient, okay? And then what you get when you take the supremum over all x and y, that you get here exactly this is e in the power of minus lambda 2 minus lambda 1 times t times the oscillation of phi 2 and phi 1 is more equal than a constant times e in the power of minus t pi squared on t squared. Okay? So that you get this number, it is important that you have a Neumann boundary condition, omega 0, and because you have Neumann boundary condition, this depends on this number. And this bound has basically it's the lower bound of the Weinberger inequality. Okay, so that's another point. But I come back to this. So, and now you see it's now you argue by contradiction. So when t tends to infinity, you have this uniform inequality in t basically. But if this one here would be smaller than pi squared on d2, then this would decay faster than the left-hand side. And so there would be a contradiction. And so for this reason, the difference, the fundamental gap must be bigger or larger or equal than this number. Is this clear? Yeah? Okay.
Let's hope.
Sorry?
Let's hope.
Okay. So that is basically the argument how you prove this lower bound, or we prove the lower bound. So now coming back to Alexander's question that this holds, really, why can it be that basically there is this lower bound is independent of alpha? And in fact, this is a non-optimal lower bound. So as I already said, the Robin problem with this auxiliary function phi satisfies Neumann boundary condition. So you have in the Neumann case, you have exactly the same argument, but the first Neumann eigenfunction, if v is constant, so v is 0, for instance, then the first eigenfunction is constant 1. So the same argument would exactly to the same bound be. Yeah, when v is 0. And so what you get basically when v is a 0 potential, you now have a different proof of the Weinberger inequality. So this is another reason why this lower bound is suspect. And in fact, the lower bound has to depend on the Robin parameter alpha. That's exactly the point.
Is this, am I right that this bound is sharp just for Neumann case?
Yes, exactly. It's just sharp for the Neumann case.
Yes. And for the Dirichlet case, it should be 4.
Yes, exactly. It would be pi squared divided.
No, 3. No. 3.
There must be a 3, yes. 3 pi.
3 pi squared. Yes. Okay.
Yeah.
It is for the case when domain is a ball, maybe more exactly.
Не, Юр, шар не оптимален, оптимален отрезок.
Отрезок, да? Саша, отрезок именно?
Да. Yeah, okay, please.
So this is just optimal in the Neumann case. Yeah. And we are lucky, we are really lucky that you see the V also in the Robin case cancels, becomes Neumann, homogeneous Neumann boundary condition. Yeah, that's the only point. Okay, so it's not an optimal lower bound. So now, but nevertheless, the theorem, it is quite difficult, and it was we took quite a long time basically to prove here this, and gave us a motivation to ask, okay, is actually every Robin eigenfunction log concave? Yeah. And so we looked for examples. Let's take first the square. And on the square, you have a separation of variable argument. You know that the eigenfunction of the square is the product of the two eigenfunctions. Phi alpha is on the interval 0 alpha, and phi alpha hat is the Robin eigenfunction on the interval 0 b. Okay, and then you have exactly the product is an eigenfunction. But now on the interval, the first Robin eigenfunction is always basically log concave, because you have minus phi double dash is equal to lambda phi. Phi alpha is positive, the first eigenfunction is positive, so the second derivative is strictly negative. So you have even strict concavity, and strict concavity implies log concavity. So yes, in the square case, you have it. Then on the ball, is the first eigenfunction log concave? Well, you have that omega is radial symmetric, so you get the radial solution. So the eigenvalue problem reduces exactly to this one. And again, you can use the shooting method and show that phi alpha is concave, and concavity implies log concave. So that's our two extreme cases. Let's say it like this. So I mean, the one was the rectangle and the other one was a ball. This let us believe, yes, one could basically assume that every Robin eigenfunction is log concave. Yeah, but this is false. So we need to confess that actually it took us over a year that we were running in the wrong direction. We were running in the proof in the wrong direction until we showed that our argument arrives to a contradiction to our assumptions. And then we understood there is something wrong. And we had to try to prove basically that the opposite is true. So in this way, so this is then the first result. So that omega, so we were looking then, how do we construct basically domains on which we can basically say, yes, there is the first eigenfunction cannot be log concave. And we know already that the rectangle, which is the simplest or one of the simpler domains, convex domains, that they are log concave. So what about triangles basically? And so on. So we try to start to looking for convex polyhedral domains. So now let omega be a convex polyhedral domain, which is not a product of circumsolids. I come to the definition in the next slides, okay? Then we could prove that for sufficiently small alpha, the first Robin eigenfunction is not log concave. And in fact, we can all classify all convex polyhedral domains where the first eigenfunction is log concave and which is not. So this was a really big challenge, basically. So what is again a polyhedron? A polyhedron is an intersection, a finite intersection of those domains, half spaces, basically. So nu I is the outward pointing normal unit vector, and there's some constants pi. So the faces are exactly when you have equality. So the faces of your polyhedron are exactly the set. One face is the set of all x in Rd, such that the dot product of x with the normal derivative is equal bi. So you start now with a polyhedral domain, we call this a circumsolid if you have a center in omega and with a ball, and the ball touches each of these faces exactly at one point. Yeah, so that's a circumsolid.
So it is inscribed in this polyhedra. Mm-hmm.
Yeah, so you see here in R2 actually, those are all triangles, by the way, all they are circumsolids, we know from primary school. Every regular pentagon is a circumsolid. The screw quadrilateral is a circumsolid, and the screw triangle. But as I said already, all triangles are circumsolids. But for instance, a quadrilateral like this one, trapezoid, is not a circumsolid because in order to be a circumsolid, there where the dotted line be would need to be one face, but it's not. So this is not a circumsolid. In higher dimension, you have, for instance, the tetrahedron or the regular dodecahedron. That's a circumsolids. But if you take the tetrahedron and you slice it at the tip, very close to the tip, then the inscribed ball will not touch the plateau on the top. And so it's not anymore a circumsolid. Is this clear? Yeah, I think that's easy actually.
Yes.
So now what is now a product of circumsolid? So there are more general domains. And as product of circumsolid is if you can find a decomposition of the Euclidean space Rd in orthogonal subspaces, such that if you take now the projection, and there are a finite number of circumsolids. So if you take now the projection on the subspace EI, and you apply it to omega, you end up in a circumsolid. So the projection of omega into EI is a circumsolid. That's what it means, a product of circumsolids.
Yeah, but it is simply a Cartesian product.
Yeah, yes.
Okay.
So, so we are not doing, that's important actually, what you say, Alexander. So it's not that we use here some change of coordinate system, okay? So the quadrilateral, so here the rectangle, for instance, in R2 you can decompose in R times R. And of course, the projection on the real lines you have here then of the rectangle on the real line is one interval. The interval is a circumsolid, trivially. And if you take the other projection on the y-axis, so that would be the second real line, then you have again an interval 0b, which is of course a circumsolid. In higher dimension, you can do the same. So you have here not the higher dimensional rectangle, and then here you have a prism. So the prism is nice basically because here you have you decompose R3 with R2 plus R. So that's R the two subspaces, R2 and R. And because the regular pentagon here, you have basically a regular pentagon which is inscribed. So it's that's in R2 basically, the circumsolid. And then the other line is an interval from, let's say, from 0 to A. Both are circumsolids. So that's a typical example of a product of circumsolid, which are not circumsolids. Okay, so here's again this theorem. So if now omega is not a product of circumsolids on such region, for sufficiently small alpha, the first Robin Laplace eigenfunction is not log-concave. Yeah, so we start with potential v equals 0. So not log-concave means there are at least 2 points x and x hat in omega bar, and there is a t naught between 0 and 1, such that you have the reversed inequality with a strict sign. And because of this strict inequality, if you know, you can use this in order to approximate a given domain omega, where you know you don't have basically where this on omega basically the log concavity is broken, then if omega n is approximated with respect to the Hausdorff topology, then we know that the eigenfunctions on omega n converge to the eigenfunction phi locally uniform. So on every ball, basically, of the intersection of the omega n's. So uniform convergence and the strict inequality, that's are sufficient to show that there are for sufficiently close omega n, that omega n to omega is sufficiently close, that for eigenfunction on omega n's, also the log concavity assumption basically breaks down. So they are also not log concave. So that is basically a consequence of this. So now the approximations, they don't have to be any more polyhedral domains. There can be, you can approximate the polyhedral domain by other convex smooth domains, but they are not necessary polyhedral domains. So you don't need any more polyhedral domains. Okay, so how do we prove this? The proof is basically what we use is a perturbation argument for this theorem too. So we know that the eigenfunction, the first Robin eigenfunction, which depends on alpha, is basically this map here is a C1 function from R into H1. And also C1 in the Hölder continuous function. So H1, yeah, because we use the notion of weak solution, and you get then, if omega is a Lipschitz domain, you get even that it is C1 with respect to the Hölder law. Okay, so then we set now for alpha and R, V alpha to be log of phi alpha. And now what we do is we compute the first variation of V alpha with respect to alpha at alpha equals 0. So remember, when alpha is 0, phi 0 is the first Neumann eigenfunction. So the first Neumann eigenfunction is because we look for normalized eigenfunctions. So with respect to the L2 norm, phi 0 is constant 1. And so log of 1 is 0. So V naught is constantly 0. So, and that's the reason. So we have now what we get then, the first variation is basically, so that is V alpha is equal, and then so there's 0, because we do the variation around alpha equals 0, times alpha V plus some small o of alpha, V converges to 0 when alpha tends to 0. Sorry. And V, so the derivative with respect to alpha, satisfies now a very interesting toy problem. And that is this constant Laplace equation. So mu is a constant. This is exactly given explicitly here. So it's a quotient of the area is the Hausdorff distance of the surface divided by the volume of omega. And gamma i's are 1. So these constant, so you have constant Neumann eigenvalue, and you have constant Laplace equation in omega. In all phases, you have the omega. Okay, so if you can now show that when alpha is close enough that the V is not log concave, then by this type of conversion, you can shift it to V alpha, basically. That is what you can do. Because of this perturbation result. So that is the reason why we are interested in basically, we are mainly interested at the log concavity conditions of exactly this toy problem, I call it, okay? TP. So, and that is where the classification of the areas start. So, let's assume they are semi-concave. So it's even not concave. Why concave? Because we already applied log to phi alpha. Yeah. So if V is concave, then phi alpha is log concave. So what we can show then is, okay, if V is semi-concave, that V is actually C11 up to omega bar. So how do we prove this? This is easy. Semi-concave means that in omega, the Hessian, so D squared is the Hessian of V, smaller or equal than a constant times the identity matrix. Yeah? So there exists a constant such that the Hessian is smaller than this type of constant. That is semi-concave. However, so what you do is now you take now vector and you, to each of these vectors, you choose an orthonormal basis. You want to D where the D's direction is just the vector E. So then with this new change of, now we change the coordinate, you can write now E transpose the Hessian of E, so the quadratic function evaluated at E, and then you can rewrite this as the Laplacian V with respect to this normal basis, new basis, minus, so you basically, you add and you subtract. Now, V solves the toy problem, and so the Laplace operator with its coordinates is constant mu. Okay? And here, you know from above that the Hessian is semi-concave. So this is smaller than a constant times the absolute value of the I squared. And that's the reason why you get basically that V is bounded from, this is mu minus C times D minus 1. And so what you have shown is that the quadratic function is basically bounded also from below. For every unit vector, and it is uniform, the lower bound. So you have that the Hessian is bounded from above and from below. And if the Hessian is bounded from below and above, this implies Lipschitz bounds, basically, up to omega bar. So you see that semi-concavity implies Lipschitz. So when it is Lipschitz, then you can show that it is C2. And for this, you need, we use basically spherical harmonics. And here, in order to do this, we need to use the structure of omega. So the point is, it is a polyhedral domain. In the inside, away from the boundary, there we have here a classical elliptic equation, so uniformly elliptic equation, and so the Poisson equation basically is nice. It's in L infinity. Of course, inside the area, it's C infinity. So what happens is we need to know whether V is basically C2 at the faces, at the boundary. If we are at an edge, we are fine. So I mean, if we're not at the edge, if we're just at the face without the edges, vertices, I mean, where if then we are also nice because the boundary is just flat there. And then we know from the nice book of elliptic, the classical book of Ladizhenskaya Uraltseva, that you have C2 up to the boundary because there's nice. So where our problems are is where two faces meet each other, or even more, basically. So that is exactly the situation. So let's assume that there are coming several faces meet at each one point. That's exactly the point. So this is basically in 3 dimensions. You see here comes a face and here should come a face. So here comes a face and here comes a face, not this above. Okay. And so this gamma naught is a tangent point at that point here. So this is omega. And the orange one, the tangent point intersected with omega is just a region, but the tangent cone would be, of course, infinite. Okay, so note we have Lipschitz. So then what we can do is we cook up a function W by V, where we fix X naught is R times Z. Okay, so basically for all RZ such that there is, we are just interested in W basically in the area, which is inside the sphere, yeah, or inside this ball. So the blue one is the sphere. So, and then you can, of course, every element there, we write it here in polar coordinates. So R is the radius, and that is basically an element on the sphere. So, and the gradient V of x0 is fixed, which exists because V is C11. And then we add this quadratic term in addition. That's the D is the dimension, we are RD times 2, and mu is the constant of the Laplace operator. Now V solves the toy problem, remember. And therefore, V is actually a harmonic function in the ball. Yeah? Because if you compute here twice the derivative, then this will vanish, but this is in constant minus mu, and this will be equal mu, and so they are 0. So in this area here, you have basically, or you can say even at z equals 1, you have basically the Laplace equation. So what happens at the boundary? So what happens at those faces? What kind of boundary conditions does W satisfy? So we go there at the face in the normal direction. So mu I is pointing in the normal direction, one here, and mu j, and this is mu I, and this is mu j in this direction. And so there we know V satisfies the toy problem, so this is minus gamma I. But here you have R times d mu, which is minus gamma I. And this is 0 because when you x goes along the faces and mu I is a normal vector, so they are perpendicular, so this must be 0. Okay, so you have that W satisfies homogeneous Neumann boundary condition at the faces and is a harmonic function. So that's good because on A, so on the sphere, on this A region, we know, okay, we can basically rewrite W as a Fourier series. In fact, we can write W exactly, we can extend W in the whole area here by Fi times R beta I times phi I. So phi I are the Neumann eigenvalues of the Laplace-Beltrami operator. And they build an orthonormal basis, of course, of L2A. So A is exactly this area on the sphere. Okay. So, and then, so this is, I skip here a step. So first, if you use this, and you want to use the Fourier transform, that's nothing else, then this would be WR phi I. But basically what you can show is you can use spherical harmonics. So the beta I, they are actually, they are radial symmetric. And so you have here this R has some special power, beta I, and you can show that they are actually solution of this quadratic equation. That's are the roots, the beta i's are the roots of this equation. Okay, and then the game is that you, when V is C11, that you show that beta I is larger than 2. Okay, that is what you show. And with this, you prove that V is basically in C2. Once it's in C2, you can prove that V is a quadratic function. Okay, quadratic, I mean really a polynomial, it's just a quadratic function. There might be lower order terms, of course. And when it's quadratic, then necessarily, oh, I skip this, okay. First I explain you how you reach from 3 to 4, okay. Let me give you here also a sketch. So the idea is, so you have V, and you know that it is C2, though you can write the Hessian already. And what you do is you prove that there exists a subspace, basically, by looking, okay, you look for the supremum, basically, of the Hessian, where it takes, but first you intersect E in the sphere intersected with some subspace. So you are looking, you prove the existence of a subspace E such that this guy is constant. Once this is constant, you can show that V is basically exactly given in this way. Where this P, this pi E is a projection on E. So because V is then quadratic on these subspace, and then after this, you make an induction on dimension. So that is the sketch basically. So then you have V is quadratic, and once you know it's quadratic, the quadratic, when V is a quadratic function on omega that is satisfying this equation, then you can exactly say, okay, V must be concave, firstly, of course, but also that it is a product of circumsolids. Okay, this I did not, I think, prepare the proof, but yeah. So now you know exactly, basically, so let us come back to this one. So V is semi-concave if and only if omega is a product of circumsolids. So that is exactly the point.
I'm sorry. Саша,
yes.
затем беру спасибо. Ну, просто насчет точности покажет сам лично. Приведи, пожалуйста.
Чуть погромче.
Насчет Кенгуру ему скажи спасибо, он покажет. Вот главное, насчет точности что-нибудь скажет. И как там Тодингер, жив или нет?
Да, все нормально. Окей. Так, окей, continue, please.
Okay, so now coming back to the statement of the theorem, the original theorem too, was if omega is not a product of circumsolids, then this equivalence implies that V is even not semi-concave. So it's, okay, it is not concave. If V is not concave, then this means phi is not log-concave. And that is the end of the proof of theorem 2. Okay? So, and we can actually do it a little bit more in certain cases. So, as I said again, phi log-concave implies that it has convex level sets. And then, of course, this proof, it's natural to ask if one can even prove that phi does not have convex superlevel sets. One could also ask this, of course. So, and here, basically in dimension 2, we can do this. If omega is not a product of circumsolids, then we can show that the first Truba eigenfunction has no convex superlevel sets for sufficiently small alpha. Yeah. In dimension 3, if the boundary points that has one boundary point with inconsistent normals, then has boundaries with inconsistent normals, then the same conclusion. So in dimension 2, you can basically always show that, well, there is this condition basically satisfied directly. But if you want to go in higher directions, in higher dimensions, we cannot prove basically that.
And what does it mean, inconsistency?
Yeah, I will explain you. So okay. We say basically, so I mean, well, let me just finish my sentence and then I come to the definition. So in dimension 2, if omega is not the product of circumsolids, then you can directly prove that the boundary points, that there are boundary points with inconsistent norms. But in higher dimension, we cannot do this. And therefore, we need this additional condition. It might be true, we don't know. So what are inconsistent normals? Say a point in omega bar as consistent normals if, and that is basically the best, so if the outward unit normals to the tangent cone lie in the hyperplane disjoint from the origin. Or if basically the tangent is an unbounded circumsolid. So the tangent plane, so at this boundary point, yeah, the tangent cone, that you can put in a ball and it touches each face of this cone exactly at one point. But of course, the tangent plane is infinite, of course. Okay, so then if this is the case for this boundary point, then you call it as consistent normals. If at x naught is not, if this is exactly not satisfied, this condition, then you say x naught has inconsistent normals. Okay?
May I say that this means that corresponding polyhedron in the sphere, the intersection of this tangent cone and the sphere,
Yes,
has is just like in previous theorem.
Yeah. So I mean, so it was exactly in the previous theorem. We say no, but there we are in a more general domain of products of circumsolids. Okay, so we should not get confused. But so circumsolids, they are automatically product of circumsolids. But here we say, okay, yes. So
in fact, the intersection of this cone and the sphere is spherical circumsolid.
Yes, exactly.
Okay.
That's exactly what it is. Yeah. So if omega is product of circumsolids, then every boundary point has consistent normals. That's what one can show. Yeah, and so you see here, this is, for instance, when you take the left-hand axis, yeah, so this is the point x naught, so we take the left point. This is an example which is has not consistent normals, because when you take now a ball and you want to squeeze it into this corner, it might be squeezed by the side faces and will not touch the upper face. So this boundary point, this vertex on the left vertex, is a point which has inconsistent norms. Alexander, does this support what you understood?
Yeah, and I have a question. If this is inconsistent, if you have all consistent normals, but it is not a product of circumsolids, the fact is not true, or you cannot prove?
No, we have no proof. We believe it is true.
Okay.
We believe it is true, honestly, but we don't have a proof.
Okay, thank you.
That's what we don't have. So that's basically the theorem. So recently has been shown a very interesting result. So these results, theorem 3 and 2, they were for very small alpha, okay? But then it's natural to ask, of course, what is when alpha is very large? So you know that the first eigenfunction of the Laplace operator is log-concave by Braskamp and Lieb. So there must be a threshold. And Krasta, Fragala, they have proved exactly that there is a threshold. But they need quite high assumptions on the regularity of the domain omega. So the boundary of omega, which must be open, uniformly convex, must be of Cm. And the m depends also on the dimension. And then there is a threshold such that for all alpha, this threshold, the first Huber eigenfunction of the negative element, is strictly log-concave. Okay, so, and then you're good. But I think that is a very good counterpart. It really complements the theory, basically, which we started. Yeah. So now, of course, it's a natural question to ask. Can one prove the fundamental gap conjecture for Robin eigenvalues without using the log-concavity. So the point is, firstly, we cannot, in many convex domains, we don't have that the first Robin eigenfunction is log-concave, so we cannot use it. But this doesn't mean the fundamental gap conjecture is not true. It still can be true. And so that is the reason why this is still an open problem which we are hunting and which we applied for a grant in Australia, and we got now funding for this. And in fact, what we could do in a second paper with Ben and Julie is that we could prove the fundamental gap conjecture in dimension 1. And let me say it again like this. So when alpha is 0, alpha is larger than minus a half here. Yeah? When alpha is 0, then you're in the Neumann case. And the Neumann case corresponds to the Weinberger inequality, and we know we have the proof for this. But when alpha is plus infinity, and alpha equals 0 and alpha infinity, all those cases in dimension 1 has been proven by Richard Levine. So, but what not has been done is the Robin case. And so this complements the theory of Richard Levine. And in dimension 1, the first eigenfunctions, they are log concave, okay? But you don't use it in the proof. It's a property which is available, but you don't use it in the proof. You use classical Sturm-Liouville theory because you have an ODE, second order linear ODE, and you just the Sturm-Liouville properties from the Sturm-Liouville problem are sufficient to conclude that the fundamental gap for any convex potential V, this Robin boundary condition, the Schrödinger operator, the fundamental gap is bounded by below by the fundamental gap of the zero potential. And this difference is very important. This difference, so the eigenvalues, they are, you see now, they're depending on alpha, and they are roots of algebraic equations. And you don't know the explicit value. You can maybe approximate them. Yes, you can do this by solving this algebraic equation, doing a Newton method, and then you can close enough.
Why algebraic?
Because remember in dimension 1, the eigenfunctions are sine and cosine functions.
Yes, but transcendental.
And when you try to do this for the Robin problem, then you will arrive to an equation where there is a tangent of...
Yeah, but it is transcendental equation.
Yes, yes, transcendental equation. That's exactly
okay.
It. So it's a transcendental equation, not algebraic, excuse me, so it's not squared and so on, but you can not rewrite like in the Dirichlet case or in the Neumann case explicitly what are the eigenvalues. So you don't know the difference even in the case V equals 0. Okay? So,
and what is the strange number -1/2?
This is a very good question.
Yeah, it is when the right quantity is 0.
No. When alpha is 0, then it is, so this alpha half comes, honestly, is a technical problem. It comes from the Dirichlet energy where you have a half. And because you have a square also, and when you do then the proof, there comes a half. We have results for the P Laplace Schrödinger operator, and then the lower bound is 1 on P.
Very strange.
Yes, and I think it is a technical issue.
Mm-hmm.
Yeah.
I think it's at the border of the coerciveness of the operator.
Sorry, I don't hear you. Can you speak up a little bit?
I think that's the border of the coerciveness of the operator.
No.
No?
No, for arbitrary alpha less than 0, it is not coercive, but it does not matter. We estimate the difference of the first and the second, the second and the first eigenvalue.
Yeah, that's right.
Yeah.
No, it's a very strange quantity, in fact. Okay.
It's a very strange quantity, and as I said, when you look in the proof, it comes from because you are having the energy, which are all squares in the linear case. Yeah. So you have the integral over a half times gradient u squared. Yeah. And also then plus v u squared and plus the Dirichlet conditions. And from those squares comes this 1.5. And you look in the proof.
Okay.
Yeah. So this is a strange number. And when you replace this by the nonlinear P-Laplace operator with Schrödinger potential, yeah, then there comes -1 on P. But we cannot prove this conjecture, the fundamental gap conjecture for general convex potential for the P-Laplace operator. There, we need to assume that it is single well and symmetric. And this has been, I think, recently slightly improved. This result when it is single well, but can be asymmetric. Yeah? So by Richard, not Lavin, I forgot, sorry, the name of the guy.
Okay.
But doesn't it? Yeah, thank you for listening.
Okay. Well, questions or comments, please?
Just a small question. I hear some computer simulations of the behavior of eigenfunctions for domains of different geometries, say for polyhedral and so on.
Well, that's a good question, but I think so. If you have a certain type of symmetry of the domain, you can always get to some reduction of dimension, and you can probably produce solutions. I can imagine. But even actually without the symmetry, let's say if you use finite element method, I think you can do numerical results for those eigenfunctions.
Mm-hmm.
And yes, this is possible. Basically.
And what does these simulations, these computations show? Is it known?
Yes, it's known. So let me tell you, I did this with finite element methods. So there is a very good program from France where they are really expert in these numerical simulations. But the problem is when you have a Lipschitz domain, a polyhedral domain, so because we were working only on polyhedral domains, the problem is it doesn't show because there are numerical errors exactly at the corners when the corners are
which are important, yeah,
which are exactly important. And so the numerical results, they break exactly at these stupid polyhedral domains if the angle's too big, and then it shows like it would be going to infinity, but actually it's the divergence C because of caused by the corners. But it's it's not accurate to the actual problem.
Okay, I see. Thank you.
And that is the problem of these the numerical simulations.
I understood. Okay, thank you very much. Mm-hmm.
Okay. So let's thank. Let's thank the speaker again.
Thank you so much.
Yeah, please stop recording.